Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend. We did some interesting stuff. Um, so I guess I should let you know we are totally done with CAD software. Completely done. We are moving on to an entirely new topic, as you can see right here. It's no more CNC machines, no more 3D printing, no more Fusion 360, no more Vectric. New stuff. We're going to be doing model. I'm glad you're excited, Cohen. We're going to be doing model rockets. And it's going to have a bit of a slow start, not going to lie to you. I got as much material as I could today, which is not quite enough to cover an hour if my middle school class is to be believed. So we'll get as far as we can. I will have more material for you on Wednesday, and we will have more material in the coming weeks. But we're going to cover pretty much as we can with model rockets in the next few weeks. That involves I'm glad you're super pumped about this. Yeah, model rockets are pretty awesome, so I don't blame you at all. But yeah, so we're going to get started with the very, very basics. Basically, what makes up a model rocket, the insides and stuff like that. Very, very simple stuff. We're going to move on to similarities between those and actual rockets, things like that. We'll go into designing model rockets and stuff. We will experience some software, OpenRocket, which is a model rocket design software. And in lab, you guys should be making your own and launching them in the next couple of weeks. So we will, excuse me, we will get through this, learn about model rockets. Hopefully you guys should find it pretty interesting and pretty enlightening. And we'll we'll just enjoy the fact that we're covering a new topic. I'm sure everybody's got a little bit of fatigue from CAD software, or you thought it was cool and you're sad to see something else. But, hey, variety's the spice of life, right? So without any further ado, let's get started with the very, very basics. Now, some of you might be looking at this and you're like, wow, this is really super basic. But that's okay. We're assuming there's absolutely no knowledge base. We're starting from square one. So we're going to go over the very, very basics, and we're going to build from there. So hopefully everything will start to make more sense as things go along. And who knows, maybe if you know a lot about model rockets already, you might be surprised by some of the information that we go over in the basics and stuff like that. Maybe not today, but, in the future. So why model rockets? And the parts of a model rocket, and eventually the similarity to real rockets. We're not going to be able to get to the similarity to real rockets today. I might touch on it, but there's not really a whole lot of material there yet, but there will be by Wednesday. So model rockets are smaller versions of rockets used in space flights. Not surprising there. Many of them emulate early rocket designs, like we're talking stuff like Robert Goddard launched. However, they can be whatever you want if you're patient enough. What do I mean by that? Well, most model rocket kits provide the means to create a very basic rocket, as in one of those very early rocket designs, but they can be customized beyond that. In fact, you can customize you can create your own custom bodies and fins and stuff like that from scratch, like this little Saturn V model rocket that they have launching off of a pad. In the picture off to the right, this is a little skull model replica of the Saturn V rocket, which I think is pretty cool. Saturn V was definitely a pretty neato rocket, and it was a pretty intimidating and impressive rocket in real life size. Just to think that, way up there, all the people being launched to space, to the moon, and back. Pretty impressive. Anyway. Why model rockets? Why not just, I don't know, do math all the time? Well, because they're fun. Really. They're enjoyable to build and launch, though there is a fair amount of frustration involved as well, I won't lie with you. But in the end, it is pretty fun. However, they can be useful, even though they're fun, to teach the basics of aerodynamics and rocket design and construction. So you can, excuse me, you can use your experience with model rockets in order to get a better feel for and appreciate more what, aerospace engineers go through when they're designing rockets to launch people into space or payloads into space. They don't necessarily have to be people, but payloads in general. You can also sort of appreciate the complexity of designs like the space shuttle and stuff like that. Even though that was an interesting result of design by committee and sort of tempering expectations and ideal situations as far as spaceflight technology is concerned. But that's a whole nother discussion for another day. Regardless, there's a reason why we had something like the space shuttle, and now, companies like SpaceX and Ariane and sorry, a few other companies are all sort of going back to the traditional rocket design. That is to say, the stick of dynamite with fins on it. There is a reason for that, and we might get more into that as the lessons go on. Just like I said, that's a discussion for another day. But the reason that model rockets can be used to teach all of these things, aerodynamics and rocket design and construction and things like that, is because model rockets share many similarities with real rockets. In fact, you might be surprised how similar they might be, at least on an overall level. But first off, let's take a look at what makes up an actual model rocket. So this is the outside of the model rocket. Exciting. Super duper complex and crazy, right? You've got a nose cone, which makes it fly through the air better, a body, which holds stuff, and fins, which make it fly through the air better. But, in all seriousness, the nose cone, helps to reduce the amount of drag on the front of the rocket, which is the part that is presumably the rocket is going to be accelerating towards. So you want to make sure that the nose, like the rocket isn't experiencing too much drag or air resistance, because that is going to slow it down. A nose cone is meant to minimize that. No surprise there, right? The body contains a lot of the recovery system and everything like that, pretty much all the recovery system. It also provides much needed structure to the rocket. Imagine having a body like your body without bones. It's sort of a horrifying thought, but that's kind of my point. A rocket without a body wouldn't really go very far. And then fins, well, fins are meant to provide stability. Just straight up, they are meant to ensure that the rocket doesn't start spinning like crazy or tumbling end over end or flying wildly off course. Fins are meant to use the air as a sort of a stabilizing point for it, whereas the nose cone is meant to reduce the impact of the air. The fins utilize the air in order to keep the rocket going in the same direction that it's meant to go in. So kind of interesting how those two, play off one another. And then not pictured here, we got the launch lug or launch lugs, which give the rocket something to hold on to. Well, basically, you've got a launch rail on a launch pad, and then the launch lugs slot onto the launch rail so that when the rocket is launching off of the launch pad, it doesn't go flying off in some random direction. Engineers are known for many things, naming things not necessarily their forte. So that's part of the reason why I said launch like a dozen times in that last sentence. Granted, I was also exaggerating it a little bit, but regardless. Anyway, the point being, the rockets generally have a minimum speed for their fins to be effective. For many model rockets, that could be around 30 miles an hour. Once they hit about 30 miles an hour, the fins can actually engage enough in order to keep the rocket pointed in the same direction. So what the launch lugs do is they hook onto a launch rail, and when the rocket is launching, they basically keep the rocket in place and heading in a specific direction until it is going fast enough for the fins to basically grip onto the air, for lack of a better term, and keep the rocket heading in the same direction. Hey, Mateo. As you can see, we're going over model rockets. The inside of the rocket, though, is a little bit more complex. It's not crazy, but, you know, it's a little bit more so. Thank you, NASA, for this wonderful diagram. Check your sound. Say that, and you say you can't hear. We'll send that out. Okay. There we go. Okay, so there are a few things going on in here. It's not insane, but, you know, it bears going through. Excellent. Glad to hear it. It bears going through at least most of these. Now, granted, this is a different diagram than what I, you know, had up here, which is basically just a picture of a model rocket that I pointed to stuff on. But this does provide some context to something as insanely complex as a model rocket. Yes. So, you know, we can take it, we can see this is the nose cone that we're talking about here. So there's actually, you know, stuff on the inside. The nose cone is actually removable. The nose cone pops off the top. There's a reason for that. The reason for that is for the parachute to come out, but, you know, we'll get into that. So you got the fins here. Here you can actually see the launch lugs that I'm talking about. A lot of times these are made out of like a straw or something like that, or just like a very simple like plastic pipe or something like that. It's not meant to be strong necessarily. It's not meant to be, you know, just, it's not supposed to have a death grip on the rail or anything. It's just meant to provide some guidance for the rocket as it's going up into the air. So they tend to be very simple. So you've got the fins, you've got the body, you've got the nose cone. That's sort of the stuff that we went over here. And you got the launch lugs. Went over that in the last slide. But the inside of the stuff, let's take a look at it. So you've got in the back here, this thing is labeled B64. That is the solid rocket engine. So the engine, as you probably can guess, is what provides the power for our rocket to go up. Now, you might be looking at this going like B64. Why is it labeled that? Or you might not be, but I'm putting that question in your head now. That has to do with the class of the model rocket engine. Model rocket engines can come in different classes, which essentially just means size. And they are denoted with usually a combination of a letter and some numbers in order to provide you, the purchaser or the user, some information about the power of the engine and the how long it's, you know, fires for and stuff like that. We'll go into detail about how to read that and what exactly that means later on, but just understand for now that the engine make the rocket go up into the air. Yeah. It's got a few other purposes to it as well. Well, a couple. But again, we'll go over the parts of the engine a little bit later on. The engine classifications and stuff like that, that's for another day, but the parts of the engine we'll go into later today. Then we got the engine mounts. Now the engine mount is fixed in place. This makes the engine fixed in place. Now the engine mount isn't removable. The engine is. So the entire point is this rocket is meant to be reusable. We can pop out the engine after it's been used and replace it with another engine, one that hasn't been fired or anything like that. The engine mount is meant to keep the engine in place in the meantime, because obviously if the engine isn't fixed in place, we could have a rocket sitting on the launch pad, we could launch the engine, and the engine just goes, you know, just shooting up through the middle of the rocket. Pops the nose cone off, goes flying off and wiggling around in the air for, you know, like a little while before it falls to the ground or shoots towards the ground because it tumbles in such a way that it goes flying towards the ground. You know, not exactly a good rocket launch. Dramatic and probably funny, but not exactly a good rocket launch. In addition, at the end of it, there's a charge, there's an upwards bit of thrust. And we want to make sure that the engine stays inside of the rocket for that as well, because it's meant to blow all this stuff out. And it's also probably not good if the engine just falls out while the rocket is like 300 feet up in the air. So the engine mount, make sure the engine doesn't go anywhere. That's basically its main purpose. The recovery wadding provides a bit of protection against the ejection charge of the engine, which we'll, you know, spend a little bit of time going over later, but essentially the engine just shoots out a bit at the top, which causes everything to fly out of the top of the rocket, thus creating the recovery stage of the rocket. So the parachute is that blue bit right there. It's meant to be a parachute, keep the rocket from falling to the ground like a stone. You thought I was going to say rock. Sort of increases the recoverability of the model rocket. Now, that's not to say that model rockets are 100% reusable all the time forever. We don't really have anything in rocketry that is. That would be amazing if we did. But, everything wears out after use. Man, if we had like 100% recovery, can you imagine how cheap spaceflight would be? Or how much cheaper spaceflight would be? A lot cheaper. Anyway, the parachute is meant so that we can at least recover the rocket body and the nose cone and everything that goes along with it. Obviously, the engine is not meant to be reusable. We're supposed to replace that after each use, but the parachute makes sure that at least everything else is reusable, so we don't have to throw out the entire model rocket every time we launch it. The shock cord basically connects the nose cone to the inside of the rocket body, and this ensures that the nose cone is recoverable with the rocket body because, again, let's say that the ejection charge blows and the nose cone pops off and the parachute flies out, and then the nose cone, which is usually made out of some sort of wood or cork or something like that, or plastic, falls from 300 feet up in the air, and it's got a pointy bit on it. That doesn't seem ideal. So we want to make sure that the nose cone stays with the rest of the rocket, A, so it's not falling on people, and B, so that we can, recover it. Because imagine, if it goes flying off and it lands like 30 feet in some other direction, and now you have to go digging through the grass to find your nose cone. Not ideal. So, we keep it attached to the body in order to make sure that everything falls down together and in a controlled way. Now, the shock cord is also specifically designed to reduce the stress of the nose cone being blown off by the ejection charge, which is to say that when that nose cone goes flying off, it goes flying off pretty quickly. The shock cord is a very elastic piece of, cord, string, cable. Not like an electrical cable, but like a cloth thing. It's like nylon or something like that. And so that's because it's meant to absorb a lot of the force of the nose cone flying off. If it didn't, well, that nose cone goes flying off, it reaches the end of the cable and immediately pulls it taut with a lot of force. That could damage the inside of your rocket. That could pull your rocket wildly off course. That could just detach from the inside of your rocket and suddenly your nose cone is free falling separately from everything else. Not ideal. So we have the shock cord in there, and the shock cord's entire purpose is to absorb a lot of the force of the nose cone being blown off. This keeps the rocket as much as we can on course and undamaged from the recovery stage activating. And the parachute lines hold the parachute to the inside of the rocket. Otherwise, the rocket would fall and then the parachute would gently float down afterwards, which sort of defeats the purpose of having it in there. And again, mentioned in this diagram are the launch lugs. Pretty simple, usually just some bits of straw or pipe to keep the rocket on the launch rail. So now, after all said and done, let's take a closer look at how the engine is actually structured. The engine comes in a few different parts, but they're all meant to serve a specific purpose in your model rocket as it launches. So you've got the clay nozzle at the bottom, which is just clay, so it's heat resistant. And it's shaped. It's just basically a little tiny like aperture. And the whole point of that is because it's meant to provide directed thrust. It's meant to provide more powerful thrust. If we didn't have that there when the propellant went off, imagine, like you've got like a bonfire burning or something like that. And it's burning kind of dramatically, like you've got a lot of logs on it, but it's still just sort of a bonfire burning. There's a lot of heat, but it's not going in a specific direction. It's not creating any sort of, thrust or anything like that for the rocket. So, propellant could still provide thrust because we're still putting it into a small engine and everything like that, but the clay nozzle just magnifies that thrust and gives it a direction so that the rocket is more guaranteed to go upwards. So that's the whole point of the clay nozzle. Now you got the propellant, which, as the name implies, is your main source of rocket go up. This is the first thing to ignite whenever you ignite a rocket engine, and it burns very, very quickly. You know, if you've ever launched a model rocket, the actual launching part, the powered part, is very short. It just goes, and that's it. And it's very fast. But that's the entire point, is it's meant to burn very quickly because the air that is inside will then heat up. You know, the heat will rush out through the clay nozzle, the fire will rush out through the clay nozzle. They'll all provide a downward force, which will force the rocket upwards, and thus you'll have a flying rocket. Then once you hit the end of the propellant, whoops, wrong direction. There we go. Now we are on the delay charge and the tracking smoke. So after the propellant is expended, the delay charge spends some time burning. It burns pretty slowly, and it burns with a little bit of smoke. And the point of that is to, you know, basically provide some smoke so that you can see the rocket. Because generally, at that point, it's decently high up in the air. It can be a little bit more difficult to spot against the sky, especially if it's like a bright day or it flies into the sun or something like that. Not into the sun, because then it wouldn't be a model rocket before it anymore. It'd be an actual rocket. But, you know, it flies so that you have to like look up into the sun in order to see it or something like that. Or if it's like one of those cloudy days where the clouds are really bright and it can be really hard to see everything against it, you know, it'll drop sometimes some colored smoke in order to be able to, so you can locate the rocket more easily. But a bigger point of the delay charge is basically just to put some distance between the propellant and the ejection charge, because the ejection charge is basically just meant to explode that clay cap upwards, you know, push out the recovery wadding and the parachute and the nose cone and all that stuff, and put the rocket into the recovery stage. However, as we all know, inertia is a thing. Newton was a pretty smart guy, and when he said that a body in motion stays in motion unless acted upon by an outside force, he really meant it. Now, our rocket will be acted upon by outside forces, namely gravity and wind resistance, or friction, I guess. But that doesn't mean that it stops immediately as soon as the propellant runs out. It's still going to spend some time coasting upwards into the air. You know, losing speed, slowing down, but still gaining altitude. The delay charge ensures that basically the rocket spends as much time accelerating, or not accelerating, but moving upwards as possible. Sorry about that. Moving upwards as possible before the parachute deploys, so we got maximum altitude. But on top of that, the rocket is moving very, very quickly as soon as that propellant is expended, because obviously it's spent that entire time accelerating. If we deploy the parachute as soon as the propellant runs out, well, A, we're going to reduce the amount of time the rocket is going to spend going upwards, and B, we're going to put a heck of a lot of stress on that parachute. You know, imagine holding a plastic bag outside the window of a moving car versus, you know, holding a plastic bag up in the air while you're running down the street. One of those is going to exert a lot more force on the plastic bag, and I'm going to tell you right now it's going to be while the car is driving down the street. So we want to, you know, make sure that we're not exerting a whole lot of force on the parachute, because again, all of this stuff is basically held together by strings, and you know, it's connected to cardboard and plastic and paper and stuff like that. So, you know, if we deployed the parachute at as the rocket's moving as fast as it possibly can, there is a possibility that the forces will be enough that the parachute gets ripped out of the body, or it, you know, some of the strings detach from the parachute because, you know, it's going so fast, and so now you have a parachute that's just only partially attached to your rocket. Things like that. Not ideal. So we want to make sure that the parachute is treated nicely, and also that it can do its job pretty well, because it will also, in essence, be keeping a rocket from accelerating from a slow position, as opposed to slowing down a rocket that is accelerating that is still moving very quickly. So that's the whole point of the delay charge. Then you got the clay cap and the ejection charge, which I've already spent a little bit of time talking about. Basically, the ejection charge just sort of explodes the clay cap upwards. It creates a whole lot of hot air right underneath it, and that hot air creates a whole lot of high pressure, because the hot air tries to basically inhabit as much space as it possibly can. So we have a normal amount of air at a normal temperature in an area that is, you know, normal for it, the air heats up, needs to move somewhere. It needs to expand in order to take up more space. It needs to increases the pressure. The clay cap goes upwards. The clay cap forces out the rest of the stuff inside of the rocket, forces the nose cone off of the top, and the parachute deploys. Now you'll notice also that there's the recovery wadding there, and that's because this all happens very quickly and is very, very hot. That's the entire point of it. So the recovery wadding is there because the parachute is generally made out of, some thin plastic or some not parchment paper, but like, some kind of like a wax paper material or something like that, some kind of delicate sort of paper. The parachute itself is very delicate because it's meant to be as light as possible while still, holding in as much air as possible. An anvil does not a good parachute make. For that reason, fire-resistant materials tend to make unideal parachutes. Now, there are fire-resistant materials which make, good parachutes, but those are expensive. Those are generally things that you and I just can't go down to the hobby shop and buy. So for that reason, we're stuck with the plastic parachutes for that. And because of that, we want to make sure that they're as protected from the heat of the ejection charge as possible. They're also protected from the forces of the ejection charge as much as possible. So that's why the recovery wadding exists there. Carbon fiber? No, carbon fiber doesn't really make a good parachute. Carbon fiber can make a good rocket body, but it doesn't do a very good job of being a parachute. I'm talking about, I can't remember the name of the material right now, but it's stuff like space-age sleeping bags and emergency blankets and stuff like that are made out of. That can make a decent parachute. Can. But yeah, so, for that reason, you want to make sure that the recovery wadding is there in order to protect everything from the force and the heat of the ejection charge. And so all of these things sort of work together in order to create a rocket that launches up into the air and gently floats back down to the ground. Gently, I say. Gently in quotes. Certainly more gently than without a parachute. So with all of that put together, a typical launch for a model rocket will likely look something like this, assuming everything goes right. So you've got the launch where it's sitting on the launch pad. The launch lugs are fitted to the launch rail on the launch pad, and then the engines are ignited, usually using an electrical charge. Like you hook up some wires to the actual engine, you flip a button, and then the wires, or you press a button or you flip a switch, the wires spark. Basically, you put the wires actually into the reusable engine for the model rocket. The wires spark. The spark is generally enough to cause the gunpowder inside of the engine to ignite, because that's what most, model rocket engines are. They're some form of gunpowder. But it causes the gunpowder to ignite. That's propellant. Then the rocket starts to actually lift off from the launch pad using the launch lugs and the launch rail in order to have stability. And then you have your power descent, which again is a very, very short bit of the rocket's launch. But still, it provides the upward acceleration for the rocket, making it do what rockets do, which is go up and then come back down. But, the go up part, certainly here. So it goes, shoots up into the air. Then the propellant runs out, and you enter coasting flight. Now, this diagram is also just mainly is a simplified representation of it. But, it's not necessarily accidental that here in the coasting flight stage, you're seeing the rocket start to turn sideways. So this is where the delay charge is burning, so you'd probably see some sort of smoke here or something like that. And also it would be much, much quieter. But anyway, it's no accident here that they have the rocket sort of starting to tilt sideways as well, because, generally when you're building a model rocket, excuse me one moment. Sorry, my throat is very dry. Um, anyway, when you're building a rocket, once you've built a rocket, the nose cone is generally pretty heavy. Like I said, it's made out of some sort of plastic, if you want it to be lighter, but otherwise some kind of cork or wood or something like that in order to provide structure. The engine in the rocket is also pretty heavy. You know, it's just a solid block of gunpowder and stuff. With the engine mounted inside of the engine mount, the rocket is generally pretty bottom heavy. However, as that gunpowder burns away, the engine becomes lighter, which means that the rocket could potentially become more and more top heavy. As it's ascending, it's still moving fast enough that the fins are holding the rocket in place, you know, keeping it pointed upwards, all that good stuff. But as it's coasting, it slows down to a point where the fins can no longer do their job effectively. And so as the rocket becomes more top-heavy and the fins become less effective, you start to see the rocket begin to do maybe a sort of tumble. It starts to point downwards in order to sort of compensate for this. Generally, though, it doesn't get all the way there because then the ejection charge blows, the parachute comes flying out, the nose cone comes flying off, you know, a lot of the recovery wadding comes flying out, and for that reason you might see people put recovery wadding in that's like purple and green streamers or something like that. So, excuse me, it looks like a party favor goes off in the sky. But all that stuff deploys, and then you can have your slow descents. So the shock cord absorbs, yeah, basically. The shock cord absorbs much of the force, and the parachute deploys, holding everything. As it floats down to the ground, pick it up and prepare your rocket for another launch. This usually involves, you know, replacing the engine with a new one and repacking the inside with recovery wadding and putting the parachute back in properly and all that kind of stuff. This is meant to be as reusable as possible. Now, that's not to say it's perfectly reusable. Obviously, you run into situations where, you know, that engine going off is going to generate a lot of heat. It can damage the bottom part of the rocket. It can cause the glue holding the fins to sort of soften and melt, which might make one of the fins blow off when you're going upwards very, very quickly. You know, the rocket itself can take damage from landing on the ground, even though it's got a parachute. It's not necessarily going to slow it down to make it a perfect touchdown. The parachute and stuff all fastened inside, that can get weaker with each use, with each time force is exerted upon it, stuff like that. You know, so it's not going to be 100% perfect, but it's going to be a pretty good, you know, representation, or a pretty good guarantee of reusability and reliability. You know, for the most part. I should also mention that. Well, let's go ahead and. Yeah, so this is all nice, but how does this compare to full-size meant to go to space rockets? Well, they're actually pretty similar to one another. Now, it's important to note that model rockets, the ones we're talking about here, are generally what are known as lightweight model rockets. They're not really meant to go above 300 feet. You know, they're not really meant to go above a certain speed. They're not really meant to be larger than a certain size, and they're generally built out of, you know, cardboard and wood, like light woods, like balsa wood and stuff like that, and, you know, paper. Like, they're meant to be very, very lightweight things, meant to be very small potatoes things. But, you know, that's fine for our purposes, certainly. If it went appreciably higher than 300 feet, we would need to consult the FAA and, you know, get a good time to launch and stuff like that in order to ensure that our model rocket doesn't fly into any low-flying airplanes or anything like that. Not a very likely event. Certainly borderline impossible at 300 feet. Something's got to be seriously wrong with that airplane if a model rocket flies into it at 300 feet, and you've probably got bigger problems as an airplane pilot than a model rocket flying into your airplane at 300 feet. But, you know, much higher than that, yeah, you definitely want to make sure that you're that you're consulting the FAA and launching at a good place at a good time, and not running into airplanes. Certainly with larger rockets, you will run into that kind of planning necessity, I should say. But yeah, so how does this compare to actual real-life rockets? Well, it might be set up a little differently, but hopefully you can see the similarities here. You've got your frame, which looks a lot like your rocket body. You got your nose cone, pretty self-explanatory. Got your structure system, which is just basically the entire rocket. You got fins, also pretty self-explanatory. Got a payload system and a guidance system. Guidance system obviously is because it's it's a fancy Dan rocket. They're going to put computers into it to make sure that it stays going where it's supposed to go. Payload system generally also involves a recovery system of sorts if this rocket is ever intended to be recovered. And then you got the propulsion system, which is nothing more than this right here, the engine and the engine mount. Now, it's important to note that this propulsion system is different. This one is a solid engine, and there are versions of those that in large space exploration rockets. You simply look no further than the solid rocket boosters that were used for the space shuttle, those two big white things on either side of the space shuttle as it was sitting on the launch pad. And that would be a fair similarity to draw. However, by and large, the basics are the same there. This is that engine, the propulsion system. You just got the fuel and the oxidizer and the pumps which mix it together and the nozzle which ignites it. As a side note, liquid engines and fuel engines are generally pretty different from one another. One of the major differences being that solid fuel engines you can't turn off. Oxidizer, because a lot of these mixtures that we have for chemical rockets require an atmosphere in order to ignite and provide thrust. An oxidizer sort of precludes that need. It makes sure that even if we were in space or at a very low sort of atmosphere like concentration, you could still burn the fuel. But yeah, so solid rockets you generally can't turn off once you've turned on. Liquid rockets you can. Solid rockets just go until they run out of fuel. Liquid rockets you can reduce the mixture, change the mixture, turn it off entirely. Liquid rockets are generally much easier to stick a vector onto, a vectored thrust nozzle onto, so you could control it much more easily. Solid, you're generally just going to have gobs and gobs and gobs and gobs of power. Like that thing's just going to turn on, and it's like being pulled by a train as opposed to being pulled by a I don't know, a person, insofar as the power differential is concerned. That's not exactly 100%. That's kind of an exaggeration. But regardless, they are solid rockets are generally much more dramatic and stronger than liquid rockets. They can also be cheaper too, because there's a lot fewer in the way of moving parts and things like that. Simply, you just start the reaction and you let it do its thing, whereas with liquid rockets, you have to worry about, the nozzles failing and the fin, or the like things like the nozzle not, the pumps failing and the nozzle not vectorizing correctly and things like that. Or vectoring correctly, whatever the proper term is. Anyway, that's neither here nor there. Point being, you got a fuel system, a propulsion system, I should say. You got a body, you got a nose cone, you got fins, you got a recovery system. You got a propulsion system, you got a body, You got fins. You got a nose cone. You got a recovery system. At the very, very sort of top level look at it, they're very similar to one another. So that's a big part of the reason why people use model rockets in order to expose themselves and others to rocket design. Anyway, that is pretty much going to do it for today, because that's the material that I have. So what we're going to do is we're going to go ahead and do the poll questions, and we'll leave it open to question and answer time. If you have any questions about anything, whether it's related to this lesson or not, I'll be here. We'll meet up again on Wednesday for the full hour, because I will definitely have enough material then for us to do a full hour of learning on Wednesday. And we will sort of get more familiar and more comfortable and more attuned to model rockets in the coming weeks. So let's go ahead and do that, so at least we can get the poll questions done, and those of you who do not have any questions can head out after that. And, you know, poll questions, regular questions, break for a couple of days, and we'll see you on Wednesday.